Welcome to Advanced Group Theory. Today we are going to explore two of the most fundamental ways that a mathematical group can interact with its own elements, left multiplication and conjugation. Understanding these actions is like discovering the hidden machinery that makes abstract algebra work, and it will completely change how you view symmetry and structure. Let us dive right in. Let us start with our first major concept, left multiplication. Imagine you are standing in a long line of people, and a director asks everyone to take exactly 3 steps forward at the same time. The entire line shifts uniformly in one direction. No one changes their relative position to the person standing next to them, but every single person ends up in a brand new spot. In advanced group theory, this uniform shifting process is an analogy for left multiplication. It is a rigorous mathematical way of describing how the elements of a group can shuffle the elements of a set, specifically when that set is the group itself. This action is always faithful, meaning every unique element creates a completely unique pattern of shifting the group around. Now that we understand what left multiplication is conceptually, let us look at its formal mathematical definition. The formula is quite straightforward. The symbol G stands for the specific group element that is performing the action. Think of it as the set of instructions, like taking 3 steps forward. The dot operator indicates the concept of acting upon, connecting the actor to the target. The symbol X represents the target element inside the group that is being moved or transformed. Finally, the result, Gx, is simply the standard group operation applied to these two elements. It shows that the action is just regular multiplication from the left side. This basic definition leads us to the first mandatory rule for any valid group action, known as the identity property. The symbol E represents the identity element of the group. This is the mathematical equivalent of doing absolutely nothing. When this do-nothing element acts upon any target element X, the result must be exactly what we started with. The equation explicitly shows that multiplying by the identity element from the left leaves the element completely unchanged. This ensures that our mathematical system has a stable baseline, where a zero-effort action produces a zero-change result. Building on the identity property, we have the second mandatory rule for group actions, called compatibility. It tells us what happens when we apply two different actions, one after the other, in a sequence. The left side of the equation shows the element H acting on X first, followed by the element G acting on that new result. The right side shows that we get the exact same final outcome if we first combine G and H into a single new element, GH, and then apply that combined element to X in one single step. This guarantees that the structure of the group is perfectly preserved when it acts upon itself. Before we move on to our next major concept, let us see left multiplication in practice with a concrete example. We will look at a simple group based on clock arithmetic, specifically addition modulo 4. Modulo arithmetic is a system where numbers wrap around after reaching a certain value, much like hours on a clock face. Our group consists of the numbers 0, 1, 2, and 3. We will choose the number 2 to be our acting element, meaning we will add 2 to every single element in the group from the left. We want to observe how this action perfectly shuffles the entire set of numbers without losing any of them. Continuing with our clock arithmetic, we will now apply the acting element 2 to our targets. In the first step, we apply it to the first element of our set, 0. Because our group operation is addition, we simply add 2 and 0 together. The result is 2, meaning the element 0 has been shifted to the position of 2. Next, we move to the second element, 1. We again apply our acting element by adding them together from the left side. The standard arithmetic addition of 2 and 1 yields 3. The element 1 has been successfully shifted to the new value of 3. The pattern of uniform shifting is beginning to emerge. Now for the final steps of this example, where the special wrapping rule comes into play. We add our acting element 2 to the target element 2, which normally equals 4. However, because our clock face only goes up to 3 before resetting, the number 4 wraps around and becomes 0. Finally, we add 2 to the last target element, 3. Normal addition gives us 5, but applying our modulo 4 wrapping rule turns that 5 into a 1. Looking at all 4 results together, our original set of numbers has been perfectly rearranged into a new order: 2, 3, 0, and 1. This proves that left multiplication acts as a perfect uniform shuffle. Now, let us move to the second major concept: conjugation. Imagine you want to tighten a screw, but you are wearing thick, clumsy winter gloves. You cannot do it directly. So you take off the gloves, tighten the screw with your bare hands, and then put the gloves back on. This 3-step process, prepare, act, undo preparation, is the heart of conjugation. In mathematics, conjugation is a way of looking at an action from a completely different perspective or coordinate system. Instead of just shifting everything uniformly, conjugation twists the group around a specific element and then untwists it. It groups elements into families called conjugacy classes, representing the exact same underlying symmetry viewed from a different angle. This brings us to the mathematical definition of the conjugation action. The formula shows exactly how this 3-step process works algebraically. The symbol G is the acting element that changes our perspective, acting like taking off the winter gloves. The symbol X is the core action or target element we want to evaluate, acting like tightening the screw. Finally, the symbol G inverse is the element that completely undoes whatever G just did, restoring our original perspective, acting like putting the gloves back on. By sandwiching X between G and its inverse, we successfully translate the action of X into a brand new coordinate system. To make this formula perfectly clear, let us look at a visual representation of the conjugation process. On screen, you see a diagram summarizing the 3 steps. The first arrow on the left represents applying G to shift into a state where the work can be done, taking off the gloves. The middle loop represents applying X, which is the actual core transformation we care about, tightening the screw. The final arrow on the right represents applying the inverse of G to return to the original state of observation, putting the gloves back on. The total combined path from left to right is the physical embodiment of the mathematical formula for conjugation. Let us see conjugation in action with a concrete example using transformation matrices. Matrices are grids of numbers used to transform shapes in geometry. We define our target element, X, as a matrix that represents a horizontal shear, pushing the top of a square to the right. We want to see what this horizontal stretch looks like from a completely different geometric perspective. To do this, we define our acting element, G, as a matrix that swaps the horizontal and vertical axes. Applying this matrix is exactly like flipping a piece of paper over diagonally. We will use this matrix to change our perspective before and after we apply the stretching action. Continuing with our matrix example, we first need the inverse of our acting matrix G. Because G represents a simple swap of 2 axes, swapping them a second time undoes the first swap perfectly. Therefore, the inverse matrix is completely identical to the original matrix G. Next, we calculate the first half of the conjugation process by multiplying G by X. We perform standard matrix multiplication, multiplying rows by columns. The resulting matrix represents a combined geometric action. First, we apply the horizontal stretch, and then we immediately swap the axes. However, this is only a partial transformation because we have not yet undone our perspective shift. For the final step of our example, we complete the conjugation process by multiplying our intermediate result by the inverse matrix. We again use standard matrix multiplication to combine these 2 grids of numbers. Look closely at the final matrix. The number 1 that was originally in the top right corner of X has moved to the bottom left corner. Geometrically, our original horizontal stretch has been transformed into a vertical stretch. This proves that conjugation successfully translated the action of stretching into a brand new coordinate system, perfectly illustrating how conjugation acts as a change of perspective. Now that we have seen how these actions work, why do we care about them in the real world? Left multiplication is the absolute foundation of Cayley's theorem, which proves that every abstract group can be thought of as a concrete group of permutations. This means we can program computers to handle highly abstract algebra by simply having them shuffle lists of numbers. Conjugation is essential in physics and chemistry. In quantum mechanics, changing your basis, which is like rotating your laboratory equipment, is represented mathematically by conjugation. In chemistry, conjugation helps group molecular symmetries into classes that determine vibrational properties and light interaction. To summarize our journey today, left multiplication and conjugation are the two most important ways a group interacts with its own elements. Left multiplication shifts the entire group uniformly, proving that every group is essentially a permutation group that shuffles data. Conjugation transforms elements by applying an action and its inverse, revealing the hidden structural similarities and families within the group. Together, they form the engine that drives advanced group theory and its applications in the physical sciences. You now have a solid foundation in how mathematical groups operate internally.